So on with the show. This is number 14 in our series of webinars, and it's a bit of a long title, but it's very relevant for anybody that's dealing with stainless steel. So that's the reason why we've put this together. I would say that there's no need to take notes. We're more than happy to distribute the slides afterwards. Both myself and Clemente's contact details will be on the last slide. So please feel free to get in touch with us if you want a copy of the slides, or if you have any questions that you've not thought about in the next 30 minutes. As Clemente said, you can ask questions via the Q&A box. Clemente will read those out at the end, and Per Oka and myself will try our best to answer them. If not, then if you think of something later on, please drop us an email and we'll get onto it. So the topic I want to talk about cleaning processes, basically, and what happens to stainless steel. So we'll start off really with where does stainless steel come from? Who invented it and when? And obviously it's very important to understand what makes a stainless steel stainless. So what is it? What are the properties that stainless steels have that make them stainless? So talking about things like colour tints. Colour tints are very relevant to anybody that's doing any kind of welding on stainless steel. And then we'll talk about the different methods for cleaning and the effectiveness of each of those. So what would we recommend as being the best method to get the best results in terms of appearance and corrosion resistance? So who invented stainless steel? We've got a lovely photograph there from an old steelworks from way back. But the guy that kicked it all off for us was Harry Brearley from my hometown of Sheffield in the UK. He discovered, it is maybe the wrong word, he invented this rustless steel. There'd been lots of people that had a go at trying to make a steel that wouldn't rust, and Harry was the first guy that was able to put more than 12% chromium into the steel. So he actually put chromium into molten iron, and the effect was that this 12.8% chromium content, when it was left out in the rain, it didn't rust. So way back in 1913 is when all of this started. So what is it? What is it about this 12% chromium in the steel that makes it stainless? Well, because there's almost like an excess of chromium in there. You've got more than 12% in the base metal, and the surface of that will react with air, and the oxygen in it will turn chromium into chromium oxide. Chromium oxide is very inert. It's very passive, and it's very corrosion resistant. So if you have a layer of chromium oxide over a base metal, then it will stop it from rusting. It will stop any kind of corrosion from happening. If this passive layer, we're talking micron thick. I mean, on this diagram it looks millimeters thick. Well, it's microns thick. If the passive layer is removed by any method, abrasive or by accident of some kind, so if that passive layer is removed, if the base metal still remains in air, then it'll reform, it'll regenerate. So there's sufficient chromium in there to create chromium oxide on the surface, and that's exactly what happens. The problem is when the chromium oxide layer is removed and there's no oxygen for whatever reason. If it's submerged in some kind of liquid, if there's no oxygen, then you can't get the chromium oxide, so you don't get the corrosion resistance. It's the chromium oxide that causes the chromium resistance. So typical surface defects that will contribute to damaging this chromium oxide layer and making the stainless less corrosion resistant. Things like heat tint and oxide. It's not just the appearance. High temperature causes oxidation of the base metal, and you get a thicker chromium layer, and it's the thicker layers, the light diffraction through the thicker layers of chromium oxide that cause the tint. I've got a separate slide on that, so I'll talk more in detail about that later. Any kind of weld defects like pores, slag inclusions, weld spatter, arc strikes, Any of those kind of things, then you're sure to have damaged that chromium oxide layer. It's a mechanical abrasion that's got rid of that chromium oxide layer. If the chromium oxide layer is gone, then you don't get corrosion resistance. If it's in air, then it will reform. Okay, but if you do have bumps and knocks on the surface, then it's an area where dirt and dust can accumulate, and that's another problem we'll talk about later again. So ion contaminations, things like from machining, especially grinding. If you're grinding and you leave grinding dust on the surface of stainless steel, then the air, the moisture in the air will attack that and cause that to rust. So that will decay, and again that decay will take away the chromium oxide layer. So everything revolves around this chromium oxide layer. Poor hygiene is a favourite as well for fabricators of stainless steel. If you have a shop that's fabricating carbon steel in the same shop that's fabricating stainless steel, then the use of the tools, whether it's brushes or grinders, shop blasters, whatever, if you're using those tools on the carbon steel and then use them on the stainless, then you're going to get contamination of the stainless with carbon steel. So you're going to put particles of carbon steel on the stainless, and that's going to get rid of the passive chromium oxide layer. Surface, I've mentioned this before, so uneven weld beads, grinding marks, these collect deposits, these accumulate rubbish, dirt, whatever, dust, and so it obviously increases the risk of corrosion, and you get product contamination. And then organic contamination, such as oils, greases, if you've got some machining oils, greases from assembly, paint as well. These can cause crevice corrosion, so it can hold moisture underneath the surface, and you get an actual crevice corrosion decay. And one of the other things about maybe thick layers of paint is that if you're going to do some kind of chemical cleaning, then it will pollute and dilute the cleaning agent. So you're not getting your true value from your cleaning agents. They're going to get diluted. So heat tint, we'll talk specifically about heat tint. So I mentioned it before that it occurs when you get the chromium-rich chromium oxides on the surface, and as you heat up the base material, so we're talking the heat affected zone that gets to very high temperatures. The higher the temperature causes the chromium oxide, the chrome, to get drawn to the surface and come out as chromium oxide, and it gets thicker and thicker, and the thicker the layers, then the darker the tint is. The one thing that has to be taken into consideration is that obviously all this chrome's appearing on the surface, and it's not for nothing. The chrome's coming out of the base material. So if you have excess of chrome, chromium-rich layers, because of the heat tint and the excessive heat tint, the darker the heat tint, the thicker the layers, the base metal immediately underneath that is depleted of chrome by definition. The chrome has to come from somewhere, so it comes from the base metal. So in order to restore the properties of the stainless steel, not only do you have to get rid of this chromium rich heat tint, but you also have to get rid of the chromium depleted layer underneath. And again, we're not talking millimeters thick, we're talking microns. But you have to get rid of that chromium depleted layer underneath, because that's vulnerable. That doesn't have the same corrosion resistance as the proper grade of base material stainless steel. So in real life, photograph of welding of stainless steel, I believe this was duplex, you can see quite clearly that in the heat affected zone you've got very serious heat tints. So very dark, getting lighter and lighter. So the darker area has obviously been hotter. As you move away from the weld, then it's getting slightly cooler, but it's still a heat affected zone. So that means that this area of the base metal has obviously got chromium oxides on the surface, and then immediately underneath you've got a chromium depleted layer. So that really is going to affect the corrosion resistance of your stainless steel. It may not be an issue for the application, but you should know if corrosion resistance is critical to the application of the welded piece, then you need to know about it. So in order to restore corrosion resistance, you've got to get rid of the heat tint, the chromium oxide layer, and you've got to get rid of the chromium depleted layer underneath. I'm sorry I'm repeating myself, but it's obviously quite important. Obviously, chromium oxide needs oxygen to form. So if you can purge the area that's getting hot, this is obviously the inside of a pipe, but it's a good illustration. If you can purge the inside of a pipe of oxygen to get rid of the oxygen, then the heat tint won't form. From number 1 at this side, you can see this is 10 parts per million of oxygen, and there's no heat tint, nothing's formed. So the chromium the chromium's not been able to react with oxygen and form oxides. Over at the other end of the scale, we've got 25,000 parts per million of oxygen, and you've got a very, very distinct heat tint there. So purging will minimize the formation of the heat tint. What you need to know is just because you haven't got a heat tint in this, like in number 1, doesn't mean you haven't got a chrome depleted layer. The heat has still gone into the stainless steel, and it's caused the chrome to move. Basically, it's caused the chrome to go to the surface, to migrate to the surface. So you still have a chromium depleted layer. You just can't see it. Okay. So obviously, heat tint is affected by a number of factors, and several of which are listed here. Obviously, steel composition. The higher the chromium content, generally, the more heat resistant the steel is, and so the heat tint colours are delayed. It sounds quite contrary, really, that you've got more chrome in the base metal and you're going to get less heat tint. But it's really the more chromium in there, the more heat resistant the steel is. So the colours become delayed. Atmosphere obviously helps. So oxygen rich means you're going to get heat tint. Exposure time causes the colours to deepen. So multi-pass welds, where the heat affected zone is repeatedly being heated up, then that will deepen the colours. And it gives the appearance that a higher temperature has been used, so it can catch you out maybe. And surface finish, so the rougher surfaces oxidize at a higher rate. So what you can see is light interference, shining through the chromium oxide. So it's very similar to temper colours in steels. The same kind of idea. So the cleaner the surface, the smoother the surface, the better it will be. So in terms of the cleaning methods, oh, here we go as an announcement, excuse me. The most common one probably that's used everywhere is pickling. Obviously, there are problems associated with pickling because it's a fairly strong acid. We've said there it will remove the oxides and the chrome depleted zone, but it'll also remove ion contamination. Didn't specifically mention it, but things like grinding dust, sparks, they're again very hot. Sparks will take away the chrome oxide layer on top of the stainless, on top of the base metal. And also they're traveling at great speed, so you've a high possibility of embedding the slivers of metal into the surface. So the iron can be actually embedded into the surface, and something like pickling will actually get rid of that. That's why it's so good and so effective. Obviously, it's dependent on the steel grade, dependent on the concentration of the pickling media that you're using, but temperature and the thickness of the oxide layer, they all have an effect, but they can all be compensated for. Pickling products, paste and gel are the usual ones. You see these kind of applicators, just brush it on to the affected areas. But depending on the size of the piece that you have, you may even have a pickling bath. Next, most common application really is passivation. So it's a mild oxidant, like a nitric acid. So this enhances, this encourages the growth of chromium oxide. What you're trying to do is to restore the chromium oxide. So air is obviously the natural primary passivation media for stainless steel. But if you treat it with this mild nitric acid, then it's NOH. There's oxygen in there, and that will encourage, if you like, the chrome to form chromium oxide on the surface. It's acid, so it will remove the iron from the surface. So yeah, it's more common to be used after some kind of mechanical cleaning. Electropolishing, this is not, it doesn't selectively choose the areas of the heat affected zone. It doesn't selectively choose the chromium oxides to attack, or the chrome depleted layer. It doesn't select those two, it attacks everything. So it's obviously a electro by definition. Again, it's a voltage and a current. You're setting up a potential difference across there within a media, and a media electrolytes, I should say, and that removes the surface. So microtips is what we call from the whole surface of the part that's being treated. So it's an electro polishing of everything. So it'll polish the unwelded areas just as much as it will polish the welded areas, the weld beads, the heat affected zones. It treats everything the same. Mechanical post-weld cleaning, not surprisingly, we see grinding and polishing, and the way to attack it really is to start off removing what you need to, basically, but then polish it up so that you don't leave a rough finish. The smoother the finish that you can leave, then the better it will be. It gives more of a chance of the stainless forming this passive chromium oxide layer, and it looks better. The appearance is obviously a lot better. We say gradually increase the grit number. So start off with a 40 to 60 when you're polishing, and then 180 and above, 360 even, to get a very high polish on there. Makes a big difference. And obviously, we say it again, it's very important that you mustn't contaminate the tools that you've been using on carbon steel. You mustn't use them on stainless steel afterwards. All you will do will embed iron into the surface of the stainless. So it'll completely get rid of this chromium oxide layer. Again, I keep going on about the chromium oxide layer, but that's what's important. Shot blasting is an option, and again, it's not selective. You're just taking off the surface of everything. It will obviously remove oxides and iron contamination, anything that's on the surface. And for stainless steels, the media that people use is glass beads mainly, iron-free silica, alumina sand. Obviously, you don't want steel shot in there for obvious reasons. And again, if it's a shop that's shot blasting a number of different alloys, then you mustn't use the shot that's been used on carbon steel. Exactly the same. You'll be blasting small particles of iron into the surface of the stainless. Exactly what you don't want. Shot blasting is reasonably common because it's fairly quick. Brushing's obviously, yeah, people brush. You can quite successfully get rid of the heat tint by brushing, and you can see what you've done, so that looks good. However, you can't really guarantee that you're going to get rid of everything, and you certainly won't you won't know that you've got rid of the chrome depleted zone. So it's a good first start, if you like. Water jetting is used occasionally, but really that's just for paints and creases. But it is a mechanical method that some people use, so I've put it on the list. So which method to choose? This is an excellent illustration. The graph is of the various treatments, the various post-weld treatments versus the pitting corrosion resistance. So the higher the number, the higher resistant the stainless is to pitting corrosion. So Number 6, we've got the wire brush. So it doesn't really matter what the numbers are. We're just trying to illustrate that for pickling is 10 times better than using a wire brush. So you've got the wire brush. Grinding is 3 or 4 times better than a wire brush, because you're sure to get rid of the both the heat affected zone, the heat tint, and the chrome depleted zone underneath. You're sure to get rid of that by grinding. When you start to polish, you can see the difference that it has between the various grit sizes from 120 up to 360. So 360, you've got twice the pitting corrosion resistance, so it's twice as good. The effect of doing a polish with a grit of 360 is twice as good as the effect of doing a grind and polish at 120 grit. And then the best of all that we recommend would be pickling. That's the best of all. That's going to give you the best results. It's going to return basically the properties of the base metal. So in conclusion, it's key that it's not just the heat tint, the heat tint that's removed. You have to remove the chrome depleted layer. That's a little bit surprising and a little bit more difficult, maybe. Chemical pickling is the best because it preferentially it grabs hold of the chrome depleted layer, and it grabs hold of the chrome oxides. So it will dissolve those regions. It's very controllable. It's relatively cheap. So it's absolutely what we would recommend. Mechanical methods, yeah, fine, absolutely, if that's all that you can do. But you do have the risk of embedding particles in the surface, so you have to be sure that it's nice and clean once you've finished doing any kind of mechanical grinding, polishing, machining. They're all risk points for actually damaging the surface and damaging the chrome oxide layer. So providing you can restore the chrome oxide layer, then this is fine. So you can do that by leaving it in air. You can do that by passivation, for example. But for optimum corrosion resistance, the absolute best that you could possibly do is to do a mechanical clean and polish, and then followed by pickling. So if you do both, then you're absolutely covered, and you're returning the material back to its original form, its original state. So that's me done. I hope that was of sufficient interest. It sparked your interest. As I mentioned at the start, these are our contact details. Please feel free to contact us if you have any subsequent questions about this at a later date. And should you wish a copy of the slides, then please drop us an email, and I'm happy to do so. The only other thing I've got to mention is the next one, which would be number 15, is a recap really on the metallurgy of stainless steel. So anybody that's involved in stainless steels, maybe not entirely, that's not a metallurgist, then I hope that one will be of interest. That's on June the 24th. So thank you, Clemente.
Thank you, Peter. Well received. As well, thank you all for the participation and the good questions highlighted. Are really nice questions coming up, guys. So I will start with the first one, which is saying this development of electropolishing methods. We have only found it effective. No, excuse me. We have. Excuse me. I have. No, here. Sorry. Have you considered the electropolishing methods that use a brush, an applicator? How effective are they? Per-Åke.
This is a development of the electropolishing method, and we have found it effective at removing the chromium depleted layer on lower grades such as 304, 316. It starts to deteriorate on 316 grades and higher alloy grades. So on 304, it is good, I would say.
Right.
Yep, great.
I come to the next question. Are you suggesting that if you purge currently, so that there is no oxygen presence, and hence no heat tint, that you do need to do a post-weld cleaning, Peter?
Yes, absolutely. It's just because you can't see where the heat tint should have been, and it doesn't mean that the chrome hasn't moved underneath it. So you've still got a chrome depleted layer underneath where the heat tint would have been. So yes, absolutely, it's still necessary. If you wish to return the metal back to its corrosion resistant state, then you do need to remove that chrome depleted layer.
All right, thank you very much.
I can add that there is always, I would say almost always, oxygen present. It's really, really hard to remove all the oxygen, despite that you're having pure argon or helium, for example. So the driving force is actually oxygen reacting with chromium. So slightest amount of oxygen will start the driving force of having this chromium depleted zone of chromium oxide on the surface.
Yeah, great. Yeah.
Super. Thank you very much. Next question. How does spatter reduce the corrosion resistance of stainless steel? Okay.
Well, you have particles normally spread around. It depends, of course, on the quality of the wire and the welding process itself. But the spatter will damage the passive layer, the chromium oxide layer. So any surface defect will attract further dirt.
Excellent. Yeah.
All right, good. The next question, contamination. If I'm using a 309 to weld carbon steel to stainless, do I need different tools than if I would be using only carbon steel? Peter.
Per-okay. Go on, you answer that one.
Okay, all right.
Yeah, that's a very good question. Well, using tools, I would avoid that because you will contaminate the chromium, the stainless steel, regardless how experienced you are as removing the oxide layer or trying to make the surface smooth. Pickling should be a better idea here. Otherwise, use two different tools, one for the stainless, one for the carbon steel. It's really tough.
It is. It's a tough one. It's a tough one, and I would agree that you're obviously going to grind and polish up your weld, but then don't use the tools on just your next 100% stainless job. But absolutely, picking would be the best option afterwards anyway.
Yeah, that's right. What you're saying. It's very difficult to mix up, but be aware that if you use a tool, carbon tool on a stainless steel, that will be a mess. The next question is, you said that even with purging to prevent heat tint, the chromium still migrates to the surface due to heat. What is driving the chromium migration if oxide isn't being formed to deplete the chromium in the layer beneath?
I think I answered that question earlier. I think you will always have extreme low levels of oxygen. But if you don't have any oxygen, the driving force is not there.
But chromium migrates to the grain boundaries anyway, doesn't it? When you heat chromium up, or heat a chromium steel up, chromium wants to migrate to the grain boundaries. That's the problems that you get with things like sensitivity. So you've got chromium migrating to chromium boundaries. Some of those chromium boundaries are on the surface. So you're still going to get the movement of chromium even though
Yeah, that's
It's not oxide, it's going to be chromium nitride, isn't it? Am I getting confused?
maybe.
Peter, you need to go a little bit closer to the microphone because you are a little bit far away. But we have understand what you said. Go ahead,
Okay.
Peter.
Please, Peroki, you will explain better.
I was just referring to the chromium oxide layer, which is the problem here that we want to take away after welding. We want to restore the chromium content in the layer underneath. So that's one thing. But maybe, Peter, you're referring to maybe chromium carbides. If the carbon is high enough, that you
yes,
will.
I am. So, yes, I am.
Yeah.
I'm just thinking about the movement of chromium.
Yeah. So it's not connected to the passive layer here that is being affected. At least my view of it.
Okay.
All right. I come to a similar question now again. If pickling is itself an oxidating treatment, albeit stronger than passivating, why is passivation still required after pickling?
I would agree with that. I mean, if you do a perfect pickling of the surface and you restore the chromium oxide, so you have a passive layer on the weld and the surrounding of the welds, and that it's the same as the base material, then you would not need to have this passivation treatment. Passivation treatment is, for example, good if you expect that you're having the plates, for example, the welded plates being outside before storage or transported to the customer. Then passivation could be a good thing. So it's more or less, you know, you have a great car and the furnish of the car is excellent. The color is excellent, but then you can leave it to the shop and have a further refurbishing of this color. It's more or less the same likeness.
Yeah, it is an activator, if you like, but chromium in contact with air gives the passivation. All right, then I come to the last one, and that says, can you please explain the physical distance of the heat depleted zone, oxide thickness, and also pickling and passivation? How long it takes for the treatments on several stainless steel, 309 versus 309L 410. What is the lifetime expectation start of rust with treatments versus noon?
Wow, that's a fantastic question. It's virtually impossible to answer. Corrosion is.
Peter, you're a bit far away from the microphone. Maybe Peroke can answer that.
It's a complex question here. I'm trying to understand it. The physical distance of the heat depleted zone, so heat affected zone, I suppose he is referring to.
Yeah.
So all from a couple of millimeters to a centimeter, maybe more, is the affected zone, the heat affected zone. Oxide thickness. I mean, you
I think
can
that
often...
they're talking about the thickness of the chromium oxide layer and the thickness of the chrome depleted zone. I mean, we're not talking millimeters here; we're talking microns, aren't we?
I mean, it depends on.
But it depends on lots of things, doesn't it?
Yes, yes, it does.
And temperature.
Yeah, and also you can. The color is also a good thing to go from here. I mean, light yellow, that is more resistant to corrosion than, for example, dark yellow. Then the layer is thicker. So it depends also how you have been welding the grade.
And to try and predict the life of something that, say, if you got heat tint on the surface and to try and predict the life of that before you start to get corrosion is what I'm saying is virtually impossible, because corrosion depends on a million different things. Time, temperature, the exposure level, the level of chlorides, whatever. There's a million things that could affect it. So you can't just say that, oh, it's bright yellow, therefore it's going to last 2 days before it starts to rust. You can't say those kind of things.
Yeah, I agree. It's a tricky question.
But a good question, yeah, thank you.
Yeah,
good question, really good question. So, but don't hesitate if you have questions. Please note down Peter and my contact as well, Peroke, from the screen. We are already now very happy to answer further questions or questions which has not been brought to the detail as your expectation. Please come back to us. We are here to support on that. With that, I will close, or we will close the webinar here. We wish you a successful rest of the day, and see you soon in the next live event in 1 month. Thank you very much.
Thank you.
thank you.